Okay, this is Kinetics and Equilibrium, Lesson 6. It is the last lesson in this unit. And our focus today are going to be what are entropy and enthalpy and how do they relate to this unit. There will be a review lesson that will be posted over the weekend, and I suggest that you work on the practice test as to prepare for the exam next week. So the first thing that we're going to talk about is entropy. It is noted as a variable delta S, and it is the degree of randomness or chaos, disorder are all good words, or messiness in a system. And nature tends to proceed to a state of greater entropy or greater disorder. So you can think about a simple process like evaporation. It's raining today, puddles form. Well, what's going to happen tomorrow when the sun comes out? The puddles will dry up. Why? Because the water went from liquid water to water gas or water vapor, which is a more disordered state. The more order you have, the less entropy in your system. The less order you have, the more entropy you have in your system. The physical state is the most significant factor in determining delta S, or entropy. So as we go from a solid to a liquid to aqueous to gas, this equals an increase in entropy. So let's use particle diagrams to illustrate entropy in all four phases. So in a solid, we know that particles are close together. They usually form a crystal lattice and they vibrate in place. Particles in a liquid are free to move past one another. They're not quite as ordered. In an aqueous state, usually molecules will dissociate. So let's use an example of NaCl solid. When it becomes aqueous, we actually have Cl minus and Na plus. And I could have drawn this simply with pluses and minuses to stick with the particle diagram. And in the gas state, as we know, particles are spread out as far as they can so that have the most entropy. Entropy increases when a compound is broken down. You're going from one thing into several things. Entropy decreases when a compound is formed and bonds are created. If there's no phase change, so we're going to look at these reactions. If there's no phase change, you're going to count up the number of molecules on each side. The rule is that as the number of moles decrease, entropy decreases, and you wind up with a negative delta S. As the number of moles increase, entropy increases, positive delta S. So for each of the following, determine if there's an increase. We're going to use I for increase. We're going to use D for decrease. And if there's no change, we'll just put an S for same. So when we look at this first one, we've got solid, solid, and gas. So you're going from an all-solid state to a mixed solid and gas state, so our entropy is increasing. And the next one, you're going from a liquid to a solid, so you're going from less ordered to more ordered, so our entropy is decreasing. In 3, you have an all-gas system, so we need to look at the number of moles of gas. You have 1 mole of N2, 3 moles of H2, which gives us a total of 4 moles versus 2 moles. So I have more moles of gas going to less moles of gas, so my entropy is decreasing. Here I'm going from solid to aqueous. We know that aqueous is more disordered, so this is an increase. Here I'm going from solid to liquid, also more ordered to less ordered. This is an increase. Here I'm going directly from solid to gas, carbon dioxide, solid, so dry ice, into the gas form. This is definitely an increase in entropy. In 7, you're going from aqueous to liquid, so you're becoming more ordered, so this is a decrease. And in the last one, you have a solid and a gas on the left going to all gas on the right, so this is also definitely an increase in entropy. Continuing with number 9, we have an all gas system. Notice we have 1 and 1, so that's 2 moles of gas on the left versus 2 moles of gas on the right. So here our entropy is staying the same. In 10, we're going from aqueous to solid, so we know solids have a lot of order, so this is a decrease in entropy. In 11, we're going from 2 moles of gas on the left to a total of 3 moles of gas on the right, so this is an increase in entropy. And in number 12, we have an all solid system, so let's look at our moles of solid. We have 3 moles of solid versus 2 moles of solid, so this would be a decrease. Even though it's in the same state, it's a decrease in entropy because there's less moles. Here we're going from aqueous to liquid, so we're going to a more ordered state, so this is a decrease. Again, we have an all gas system, 2 moles versus 2 moles. They're staying the same. And in the last one, we're going from gas to solid. Please remember that this is deposition, and this would be a decrease for sure because we're going to the solid state, which is the most ordered state. Okay, the last thing that we need to look at is the word enthalpy. Enthalpy is delta H. The energy in a system is what we're talking about, and nature tends to proceed to a state of lower energy. So in nature, this is important, we're going to move toward higher entropy and lower enthalpy, or energy. And lower enthalpy or energy refers to an exothermic reaction. And they always love to ask this as a multiple choice question on the regents. So exothermic reactions, we know, release energy and move to a lower energy state. Most common types of reactions, they are because less energy has to be put into it to get it started. So therefore, it means less activation energy, which is, you can see right here in this diagram. This is an exothermic reaction, and there's less activation energy in the exothermic state than it would be if we were looking at the endothermic state. You can just compare the size of the arrows here, which are denoting the activation energy. In endothermic reactions, we know that energy is absorbed, and we move to a higher energy state, meaning a higher activation energy is needed to get the reaction started. This is not as common because we have to put energy into getting the reaction started. So you can see that in this diagram, this was the endothermic. Look at the size of this activation energy here. Okay, to finish this up, I have a little video clip that I want to show you about entropy.
There's one last thing that we're going to discuss about thermodynamics. It's entropy. Entropy is the measure of disorder of a system.
Suppose that you do nothing to clean up your room for a year. You never make up your bed, never put away any clothes, and you never pick up those cheese balls from the floor. Well, after a year, it would be a very scary place to live. So after a year, the entropy, or disorder of your room, would increase, because you put no energy into keeping your room neat. Just like your room, the vase that you smashed earlier also increases its disorder. The glass was more orderly before it was broken than after. We represent the change in entropy with a delta S.
Entropy.
The fragrance of disorder. Entropy.
It's everywhere.
And just like when a substance changes from a liquid to a gas, when it's in a gas stage, there's more disorder, because gas molecules are in more disorder than the more closely held together liquid molecules. And molecules in the liquid stage are in more disorder, so they have greater entropy, than molecules in the solid stage.
This can be seen if we restate the second law of thermodynamics. Remember, we first stated that the second law of thermodynamics said that heat flows naturally from a hot object to a colder object, and heat will not flow spontaneously from a cold object to a hot object. With entropy in mind, the second law of thermodynamics can be restated as, natural processes tend to move toward a state of greater entropy.
In other words, everything in nature is moving towards disorder. The change in entropy can be expressed as the amount of heat added to a system divided by the temperature, or delta S equals Q over T.
But for entropy, temperature is not measured in degrees Celsius, as we've seen before. It's measured in degrees Kelvin, represented by a capital K.
The temperature in degrees Kelvin equals the temperature in degrees Celsius plus 273. So the freezing point of water, 0 degrees Celsius, equals 273 Kelvin degrees.
So, if delta S equals Q over T, then delta S is measured in joules per Kelvin.